ఎవరండి? ఓకే. బాగుంది. మరి తొందరగా మంది అయిపోగొట్టుకొని వచ్చుకుంటాం వెళ్ళాము లేనప్పుడు కిందికి పోయి పిల్లగాడు నిన్న ఒకడు అడిగిండరా నన్ను కంప్లీట్ చేసి ఝాన్సీ మేడం ఫోన్ చేద్దాం ఫోన్ చేసి
Hello,
స్టార్ట్ అయితే
check,
మేము
check.
ఇచ్చుకున్నాం.
Hello. Hello, sir. Am I audible?
Yes, yes, I can hear. I can hear you. What about you? Can you hear me?
Hello. Good morning, sir.
Good morning. Can you hear me? I can hear you without any problems.
Sir, we are just checking, sir. Just give us 1 minute, sir.
Sure, sure, no problem.
Hello. 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 హలో హలో రాట్లా. హలో హలో
Hello? Hello? Hello, sir. Sir, am I audible?
హలో హలో
Okay, thank you, ma'am.
Yes, yes.
Good morning. We welcome you all to the second day of ICACS 2023. It is an honor and privilege to introduce Dr. Raghavarao Mukamala Garu, Director of Center for Business Data Analytics at Copenhagen Business School, to you all. Dr. Raghavarao Mukamala is the Director of the Center for Business Data Analytics and Associate Professor at the Department of Digitalization, Copenhagen Business School. He is also the study line coordinator for the new master's program in data science. His current research focus is on the interdisciplinary approach to big data analytics, combining formal or mathematical modeling approaches with data or text mining techniques and machine learning methodologies. His current research program seeks to develop new algorithms and techniques for big data analytics such as social set analytics. In addition to the development and management of new master's program in data science, he is also teaching several courses in the areas of programming, machine learning, and blockchain technology. He holds a PhD degree in computer science and an MSc degree in information technology, both from IT University of Copenhagen, Denmark, and a Bachelor of Technology degree from Jawaharlal Nehru Technology University, India. Before moving to research, Dr. Raghavarao Garu has many years of programming and IT development experience from the Danish IT industry. His primary research areas include cybersecurity and cybersecurity analytics, blockchain-based technologies and smart contracts, computational social science, big data analytics and social data analytics, fuzzy logic and soft computing, formal methods for business processes and workflows. Welcome, sir. It is indeed an honor to have you here today. Please join me in welcoming Dr. Raghavarao Garu to deliver the keynote speech.
Thank you so much for a kind introduction. I hope I'm audible, right?
Yes, sir.
So yeah, I will put it in. I will share my slides. So let me. Okay, can you see my slides?
Yes, sir. It's coming.
Okay. Okay, so thank you for an introduction. So today, what I will do is I will talk about ChatGPT and other kinds of generative models. So, and what are the opportunities and the risks. So, a bit about myself. As was mentioned, I have been working in industry before moving to academia, and then. My PhD was on formal models for business processes, and I moved to CBS around 2015. And since then, I moved my research to more applied research. So now I'm working with a lot of machine learning and other kinds of applied areas. And I got tenured at CBS in 2017. And 2018, we started a new master's in data science program. And then since 2019, I've been also the director for Center for Business Data Analytics. And research-wise, I have been working with data science, mostly in the applied area, and then a lot with natural language processing and generative models for last 4 to 5 years. We have several projects going on generative models and things like that. And I also work in blockchain and smart contracts, where we have some funded projects and things like that, and cyber security, especially looking into cyber harassment and hate speech. And this is also one of the main research areas. So Copenhagen Business School, brief one slide about Copenhagen Business School. It's a public funded social sciences university in Denmark, which is more than 100 years. And it is triple accredited. And then the rankings wise, it might vary from 10 to 15, depends upon what type of ranking system and things like that. But we have around 20,000 students, and 4,000 out of them, 4,000 international students, and only 2% of the international students, they pay tuition fee here. And for all European students, the tuition fee is, there is no tuition fee, it's free education offered by the government. And we have around 800 faculty and 200 PhD students, so that is mostly in the university. And we are hugely research-based organization, so there is a quite heavy focus on research, and also quite huge focus on integrating our research into teaching. So that is the main thing. And regarding the Center for Business Data Analytics, so our main overarching goal is that how could we use digital technologies to support sustainable development and sustainable development processes. So this is the overarching research question we pursue. And we have been focusing mainly on 3 areas: data science and computational social science, working with a lot of social data, and blockchain, distributed technologies, and cybersecurity. Especially, we have several projects in cybersecurity, but mostly focusing on the social side of the cybersecurity, where we are focusing on online harassment and hate speech identification and other kinds of things. So the center has been there for the last 5 years, and we also have been very active in getting funding, because that is the only way how we fund our research and things like that. So, and then we also publish heavily. We have been publishing around 67 publications, and many of them, they belong to top ranking journals like FT50, AJG four star. But we also publish into IEEE and ACM. That's where mostly our research is focused on. And we are responsible for teaching the data science program at CBS. Now it got quite popular. So now we take yearly 100, 150 students. So, and most of our students, around 60 to 65% of the students, they're coming from outside Denmark. So, for example, Germany and Norway, Sweden. So the program got quite popular and we receive a lot of foreign students, which is also really good. We get really good quality students. And we are two tenured faculty and three assistant professors and four PhDs. And now the center has been renamed and being extended as the Center for Data Science and Cybersecurity to give a good research cybersecurity, which is one of the important emerging areas nowadays. And we also work with a lot of industry, especially we work closely with, we have a pro bono collaboration with UNHCR, United Nations Refugee Commission, where we help them on a lot of data analytics, especially looking into the hate speech and bias on the refugees and things like that. And then we have some collaborations with the local industries like Dance Bank, Capgemini, and PostNord. Research-wise, we work closely with several Danish universities, local Danish universities, and we also work a few universities in Finland, Norway, and in India, we have a pretty good research collaboration going on with IIM Nagpur and IIM Vizag, and then a few other universities where we are building up research collaborations. And before going further, I would like to briefly mention about my experience with generative AI. So basically what we have been doing in last 4 years. One of the important work which we pursue is my PhD student. So who is looking into the whether AI-generated content, AI-generated fake content, for example, fake profiles or fake tweets are generated by the AI, is it easy distinguishable from the real content? So, and this is a work going on. So where we use GPT-3 to generate fake profiles and also fake tweets, and then we combine with the real content to show it to people to content experiment how far the humans are good in identifying the AI-generated fake content. And it turns out to be very difficult. And so this is the PhD work going on right now. And then recently we also published a paper on champions for social good. So this is again a pro bono collaboration project with the UNHCR, where we try to see how far the ambassadors engaged by the UNHCR, for example, Angelina Jolie and many prominent actors and football players, they are engaged by the UNHCR to spread the message on the refugees and the refugee events, for example, Iraq and Myanmar and other kinds of refugee events. So we look into the work, seeing that how far they're effective in their message in spreading about the refugees. And it got published in a quite high-ranking journal, but where we used one of the large language models, one of the initial large language models that and basically we used it for training the downstream tasks, especially building the classifiers to identify the attitude and sentiment over the refugees. And then again, a couple of works under publication. So one is trying to understand how the refugees are framed in the news media, especially, and how refugees have perceived across different countries. If you think about refugees, the way of reception in Europe is completely different than other countries. Again, many times it boils down to the local conditions and how far the refugees have been seen as a threat and things like that. And then again, another work is focused on trying to identify the hate speech on refugees. Again, here we use a lot of large language models. Again, most of them are open source large language models. And one of the recent works which we looked into it earlier this year is the prompt injection attacks on large language models. For example, let's take the chat GPT and how to trick the chat GPT model and output something which is it's not supposed to output and things like that. Interestingly, there are still a lot of you can say loopholes or workarounds so that you can trick the model and then output something which is not supposed to do. And this is again is ongoing moving target kind of thing. Again, then you have a new large language model, and then it has to be tested and things like that. So this is prompt injection attacks which we look into. And then, the expectations for the talk is, I'm not going to talk about whether ChatGPT and other generative AI models, good or bad. Of course, nobody knows yet because the state of art in this field is evolving a lot, and we have been foreseeing a quite highly unimaginable capabilities for the generative AI. But rather than what I will do is why and how these models have become quite popular recently. And of course, there is research on machine learning going for last 40 to 50 years, and especially in the last 20 years, we have seen amazing progress on the deep learning. But all of a sudden, why there is huge buzz around ChatGPT and other kinds of models. And also, I will focus on what capabilities do they have, and then maybe we can infer what are the opportunities and possibilities that they can offer us. So this will be the overall outline for my talk. So why and how these pre-trained generative models got so popular recently. So I would, of course, there might be several reasons, but I would also want to focus on two specific reasons: these transformer models and attention mechanism, and which has been one of the recent 2017 invention and things like that. And also, I would like to focus on the another thing, self-supervised learning. So this is some sort of self-supervised learning, which actually help us to generate huge amount of training sets for feeding into these models. So this is called the large pre-trained models, and this is also an important step milestone in the generative AI. So now all of a sudden we can feed all the content available in the world to the models and things like that. And then I will quickly touch upon some of the popular large language models. And then I will discuss about what kind of opportunities we have in future using these large language models. And then again, what are the challenges and risks associated with it? So the technology always have both opportunities and challenges if we don't use in the right form. And then finally, I will conclude. So, before going further, I would want to clarify some jargon because many times people use different names for these models. Some people will say that generative AI, and if you look into the computer science and machine learning community who are active in the research, they call it as foundational models. And normally they're also called pre-trained large language models because you use a huge amount of computing power and also huge amount of vast amounts of data sets to pre-train that. So I just want to recap some of the definitions. And so generative AI, it is it's a sub branch of the AI, you can say, machine learning research, where rather than focusing on a subtask, rather than a classification or something like that, here we focus on generating new content. For example, generating images and speech and text, and so the focus is more on the generating the new content. Again, by manipulating the pre-existing data, so you have some kind of data set to feed into it, so that the machine learning models they can learn from it. So that is the main purpose of the generative. Of course, the generative AI is not a new concept. It has been there for last maybe 15, 20 years, and even before that. But it has been there. It evolved over the last decade and things like that. But what made it significant is the latest approach on transformer models. So especially we have seen a lot of amazing achievements in the last couple of decades on the image processing and how deep learning is quite effective in the image processing. And now, if we think about the self-driving cars, which is going to be a reality maybe down the line of 10 years or something like that, and that could be attributed to the latest achievements in the deep learning and things like that. But on the other hand, deep learning models, they suffer to handle natural language processing because of the language has its own characteristics and things like that. So in the last 20 years, people tried to apply deep learning models to NLP, but there wasn't being huge success with that. There was an incremental increase in the capabilities of these models, but not exponential. But all of a sudden, this transformer model, which is a new way of understanding the analyzing the text, which actually gave a lot of power. I will show you some examples and things like that. And then the large language models, people call it as LLMs, and these are nothing but the transformer models, transformer-based models. And then they explicitly trained on huge volumes of the textual data. So, and also they are quite huge models. So now we are talking about 1 trillion parameters. For example, GPT-4, I think it contains 1.7 trillion parameters. So these are the quite vast models containing several thousands of layers in the deep learning models and things like that. And the reason why we call them as the foundational models is that these are the pre-trained models. What we do is we use these pre-trained models for fine-tuning them, for example, using zero-shot learning or few-shot learning and kind of thing to specific downstream tasks. For example, identifying the hate speech or and sentiment analysis and things like that. Or you can also apply domain adaptation. So making the model to understand a specific domain, for example, on cybersecurity or whatever the domain, you can adapt these models to the by using domain adaptation techniques so that you can analyze the text in that particular context. So that's why we call them as the foundational model. So you can build a lot of applications or complex models on that question answering, sentiment analysis, and maybe. And let me quickly bring up what are the challenges with the language modeling. Language modeling is not new. It has been there for quite several years, at least a few decades. People have been trying to use machine learning for understanding the text and things like that. And language modeling, they works on the probabilistic models. So they basically, it works on the condition property. To give a brief intuition how they work, for example, let's say that we have a sentence saying that its water is so transparent. And the way we guess what is the next word which can occur after the sentence, its water is so transparent, basically we will try to compute the conditional probabilities of each word occurring. For example, occurring the probability of it and then water, conditional probability of water after it has occurred and things like so. What we are trying to do is we are trying to compute the conditional probability of that sentence occurring in exactly the same kind of thing. So that's why these models have been successful, but they are not amazing because they have their inherent problem. If you look into the application of these models, we have been already using language models in many applications. So, for example, while chatting on your mobile phone, you have this auto correction, or you can say the auto help and things like that, which gives you a bunch of words. They work on the large language modeling. They work on the language modeling and things like that. So one of the main issues with the large language model, the probabilistic language modeling, is that the data sparsity. The way we build these models is when we want to look for the examples, we expect that the same kind of the exact pattern of the words, combination of the words, they should occur in the data set. So that's why you don't find a very good many instances of the same combination of the word unless they are very common sentences. So I'm happy, I'm sad, and these kinds of words, they are quite common. So probably you might find evidence in the huge database, huge corpuses for exactly the same kind of occurrences. But otherwise, it's really damn difficult to get the huge training sets for it. So that's why they have been quite okay, but not amazing these years. And then I would also try to bring up some examples about what are the challenges with the NLP and especially machine translation, which is one of the very critical tasks in the natural language processing. So let us take a simple example where we try to convert text from English to French. So it doesn't work like that. For each word in English, we pick a word from French and just we replace, then we'll able to translate the sentence. It doesn't work like that because Many times, a sentence, a word in one language, for example, we have a growth here in this sentence, it might actually relate or equivalent to several words in target language. So the machine translation has been quite difficult, especially if you have been living in a foreign country like Denmark, then you will definitely experience the use of machine translation. So I have been a quite heavy user of the Google Translator, and the kind of the power they contain during the years of 2005 and 2000, around 2007, 2008 is very, very limited. But now these models are quite accurate and things like that. So the main challenge of the machine translation is that you don't have one-to-one correspondence between the words. And on the other hand, you also have a lot of syntactic and semantic rules for languages, which is really different across different languages. And the second example, which I want to bring up, is here we have a long sentence. For example, Griezmann's announcement. Griezmann is a football player. I think French football player, quite popular football player. Griezmann's announcement comes as a bit of shock of enduring the drama surrounding his potential last summer. Many thought that he would be committed to Atletico for more than a year, but the Frenchman seems to have never changed his mind. So the reason or my main focus point here is you can see this is a long sentence, and we can see that Griezmann was referred several times in the sentence. For example, you can see here his, he, and his, and again we have the Frenchman and things like that. And for us, it's easy to understand that all these references are pointing to the Griezmann, who is a football player, right? But when you train the models, machine learning models, it is very difficult for the machine learning models to understand that all these references, they are again pointing to one person, and many kinds of things, right? So this is one very big uphill task for machines to understand um, these kinds of things. Again, I will bring up one more example. So here we have a very simple sentence. The animal did not cross the street because it was too wide. It's a very simple sentence. There's nothing complicated going on. Very simple sentence. The animal did not cross the street because it is too wide. Let me ask you, what is the it means here? Whether it means the street or whether it means the animal, right? So again, for humans, it's not a big challenge because, of course, it can mean to both street and animal because it has references to both the things. Even if you use language parsing or dependency parsing, it can refer to both sentences. But the way we resolve this is we use our intuition, we use our common sense. For example, we know that animals are not much wider than the streets. Normally, the streets are much wider than the animals. So we come to a conclusion saying that, okay, it is probably it is not the animal that is too wide, unless we are referring to a case where we have a big elephant and a small street and things like that. But in general, our intuition and our common sense will say that, okay, animals are much smaller than the streets. So I could easily conclude that the it refers to the street rather than the animal. Of course, it is easy for humans because humans have a lot of brain processing power and a lot of power to resolve a lot of complexities and things like that. But when you teach these kinds of things to the algorithms, it is very difficult because teaching this type of common sense or intelligence, or you can say intuition, to the algorithms has been a problem till recently. So that's why the application of the deep learning models have been quite popular in many domains, and NLP is one of the last domains where it has been popular. And the main task of the current research is about teaching this intuition and intelligence because the language is always very ambiguous. And we are quite creative in writing the language, so there will be a lot of ambiguity and creative ways of writing the language. So let me quickly bring up the transformer models, and what the transformer models tries to solve is they try to solve this problem of teaching this kind of common sense. Of course, they didn't solve completely, but at least they made a big leap in making the language models to understand this type of complex intuition and common sense, right? So this is a famous popular paper, Attention is All You Need. And this is published by the Google research, and it's one of the very, very influential papers. So, and then basically it talks about two important things. Like it proposed a transformer. Transformer is nothing but it's a combination of auto encoders and auto regressive models. Especially these are the deep learning architectures, and then basically it's a combination of auto encoders which try to understand, which try to represent the words in the context of word embeddings, or you can say vector representation of words. And auto-regressive language model is nothing but it tries to generate language based on the current word. It tries to predict what is the next word, and that's how it generates the text. And regarding the evolution of these models, it was came into popularity 2017, and then after that, you can see a lot of models were large language models were built because the transformer mechanism is really efficient in identifying and understanding these kinds of dependencies between the words. So that's why they have been quite popular, and we know that ChatGPT has been quite popular, and it bring a lot of buzz from the common people as well in understanding these models. So what is the attention mechanism? It's a bit complicated. I don't go into all these things, but I would again revisit this example. So the attention mechanism, what it does is it will try to help us to rather than, okay, let me tell it like this. So people have been trying to use deep learning models on the NLP. So they have been using recurring neural networks and LSTMs and other kinds of things. But those kinds of models, for example, if you take the RNN, it tries to focus on all the words, trying to understand, trying to connect, tries to pass the single word and things like that. So on the other hand, transformer models, they what they do is, for example, let's say that now I am passing the word it, then rather than focusing on all the words that occurred in the similar context, they will try to focus on few words which might have a good relevance to them. So, for example, in this case, if I am passing the word eat, then I will be maybe mostly focused on either street or animal, because these are the two things which might have relevance to the eat. So this is how our human brain works. So basically, the transformer mechanism, it tries to address and it tries to address this problem, and it was a quite huge success. And again, let me give one more example. So this is a output which is generated by the large language model, you can say. And let's say that we just gave an input saying that as we asked the large language model to write a story for us, and we just gave input saying that as aliens enter the planet, and then let us say it automatically generates a story, right? So, but the point which I'm trying to make is, so you can see here, the way it generates is it takes each word and it looks into the context and see which word is more probable in the next sentence and things like that. But there is a lot of the attention and focus mechanism going on behind here. So you can see here as aliens enter, and began to colonize the earth, and a certain group of extraterrestrials began to manipulate the society, blah, 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 right? So basically, they try to generate the story. But again, my question is, why did they generate a depressing kind of story? Because our time machines contain the same thing. We have several novels. All these models are pre-trained, right? So unused corpuses. And we have several more, novels or the written content which talks about the aliens coming to the earth. And then many people say that if they come to the earth, then they will make us alienated and things like that. So the model picks up from what we have been fed into fed into these kinds of things. Okay, so let's again focus more on this semi-supervised learning, which helps us to train these models much more effectively. Right? So we know that what is supervised learning. You have labels, and what you do is you teach the algorithm using in the form of by giving some examples of the training examples where you have labels for the data, and the models will learn it, and then when you send new data, they will classify. So this is a common thing happening in the semi-supervised learning. In case of unsupervised learning, you don't have any labels, and you apply machine learning algorithms to group the data, and then you have some kind of clusters, or you can say segments, and based on the type of data, which is pretty standard. And the self-supervised learning, which has been quite popular in the recent decades. So one of the big challenges in NLP is generating the labeled data set is a big challenge. You have to, humans need to spend a lot of time in preparing the training set. So generating a huge amount of the data sets is practically impossible, you can say, good training sets. So then we used a semi-supervised approach, and by using that, you can generate huge label data set from the pre-trained models. What we do is we download, for example, we download all the pages from Wikipedia, and we download all the English novels and things like that, and we write a program to break them into sentences, and then all of a sudden you have huge amount of the corpus, or you can say huge amount of training sets which can be fed into the models. So this is another big step, or you can say milestone, in making these models quite popular, because now all of a sudden you have a huge capability to convert into vast amount of the examples into a proper training set. So, for example, GPT-3 used all these things. So Wikipedia, all the Wikipedia corpus and all the books corpus, and also it crawled a lot of web pages from the internet and things like that. So you can see here which contains 14 billion tokens and things like that. So this is what compromises of the training sets. So to give a bit example about what is self-training, I just take from the web. So let's say that we downloaded all the content and we split them into sentences. Now we have a sentence saying that a quick fox jumps over the lazy dog. Then what we do in case of the self-supervised learning, we take a word, for example, in this case, fox, and we replace with a mask token. So 80% of the times we put a mask token here in place of fox, and 10% of the time we replace the fox with a randomly chosen word. For example, in this case, coffee. Then the sentence will become a quick brown coffee jumps over a lazy dog, right? And 10% of the time we just leave the fox there. We don't make any changes. And then what we do is we train the models. These transformer models or deep learning models, whatever it may be, and then use these are the input data set, and we ask the model to predict this. What is the mask token? So what is the suitable word you can suggest here, right? So, and then it might give a list of probabilities, list of say words with probabilities. For example, a Jew could be probable with 1%, and maybe a fox could be a higher probability and things like that. So this is how we teach the model about the syntax and semantics of the language, and so it learns from the huge amounts of corpus. The second example which I want to give you is, so we also split them into sentences, and we feed them into the sequence of sentence. We ask the model to whether, given the two sentences, whether the second sentence is a sequence to the first sentence or not. So, for example, here we have a sentence saying that the man went to the store, and the second sentence is he bought a gallon of milk, right? So the man went to a store and he bought some milk. So these are the two sentences. And since we know that these two sentences occur in the corpus adjacent to each other, we say that this is a sequence sentence. So we say that we give a label saying that is next, and then 50% of the cases we randomly pick the sentences and put them next. So, for example, the man went to the store, and then the second sentence is penguins are flightless birds, which is completely random sentence chosen from the corpus. And then we say that these two sentences are not adjacent, or you can say not next. So this is how we teach the model, saying that what is predicting what is the next sentence. So predicting the tokens and predicting the next sentence, and this is how we teach the algorithms about the language syntax and semantics. So this is a very involved, of course, it also involves a lot of similar and complex planning processes, but this gives a very good example about how we teach the large language model, or how we teach the language model, machine learning algorithms using a huge amount of self-learning corpus. So let me quickly wrap up some of the large language models. It started in 2017. And one important thing which I want to make sure is the initial models were like a very small models. Small means relatively, these are with 100 million parameters. And now, if you look into some of the large, recent models, now they were into 1 trillion parameter, 1.7 trillion parameters, which is like a, you can see here in the last 4 to 5 years, the number of parameters increased by 10,000 times. So that is where this model, the power actually coming. And again, there are quite many huge models have been developed. Some of them are open source. For example, BERT and all these kind of models were developed as open source models by the Google and other kinds of people. But you can also see that there is a huge amount of models which are developed on the private sector. For example, OpenAI and other kinds of big companies are heavily focused on the research on it. And then, the models have been quite popular because of their huge amount of processing power, and also the amount of corpus which they use using the self-supervised learning. For example, GPT uses almost 1 trillion tokens and things like that. So that is also one of the reasons why these models have been quite popular. And showing amazing results and things like that. So I just want to show you about the capabilities with the ChatGPT. You might have seen many times this one. So here we input 3 pictures. One is an iPhone, one is a phone connected to a VGA connector, and the second one is a VGA connector, which we usually connect to monitors, our computers to the monitors, and this is a pack containing the VGA connector, right? So we fed them this input to the model, but on the other hand, ChatGPT is able to identify that we are trying to make a humor because you don't use a VGA connector which has 15 pins to a mobile phone and things like that. So they have intuition. We can see that their intuition has been developed recently very high, and they also quite good with the mathematical operations and things like that. And then I want to bring up another model which has been quite popular in the recent days. It's called the Palm from the Google brain. So these models have exhibited amazing kind of power, you can say here. For example, they're quite good in logical inference. Let me take this one. The input is Shelley is from Virginia, but she's visiting the city with the famous market where they throw fish and going home next Tuesday. And then we ask a question: is likely that Shelley will be near the Pacific Ocean this weekend? So here we give some input data and we are trying to query some intuition, right? But it contains several levels of logical reasoning here. So first of all, we need to find out where they throw fish in the market, which is in the Seattle. And the Seattle is on the west side of the US, so Pacific Ocean. And then we also infer that Shelley is going home next Tuesday. So that means she's staying in Seattle for the weekend. And the model were able to identify all these facts, and it was able to identify and put them into logical, multi-level logical inference. And then finally it says that, yes, based on the input, it says that it looks like Shelley is going to visit the Pacific Ocean, right? So this is the capabilities of large language models, which now they are able to handle large logical inference, especially in the multiple levels. So let me quickly, I can go through some of these opportunities which we have. So for example, we use them for a lot of many downstream tasks. For example, we can use them for sentiment analysis, question answering, and many kinds of, right? So, and not only that, you can build, for example, tax GPT, which can do your taxes and things like that. So, and another good example is Iceland, which is a small country in Northern Europe. They, their population is very less, 300, 400,000, or you can say 3, 4 lakhs. And they were really worried about the language will become extinct. Now they are using ChatGPT to protect the language so that it can generate content and things like that. And the second thing is, we will see a lot of AI-infused applications in future. So, for example, code generation now has been becoming quite easy. You can ask ChatGPT to write the Python code, and then it gives you. So, in future, a lot of content generation is going to be automated. So, for example, the blur between the content users and developers will erode away. So, because then it is easy for people to use these models to generate code and automatically put generate websites and things like that. One of the main opportunity which we have is in the healthcare and biomedicine. So healthcare is a quite complex domain where you don't not only have the normal text and other kinds of sources, you also have multimodal input. For example, you have X-rays, you have the patient records and other kinds of data sets and things like that. And the models will be quite popular in this area because of the capability to understand multimodal data sets and things like that. One of the things which might turn into future is the personalized medicine. Now we follow the one size for all approach. So that means we use general medicine, you can say general treatment process for all the medicine, all the diseases, right? So based on the disease, you will use the medicine and things like that. But personalized medicine is something which is really emerging practice now, based on your genetic profile, your genome sequencing and genetic profile, and it will suggest you the right medicine with the right dose and things like that. So each individual person, the medicine and the drug might vary based on their genetic profile. So this requires a huge processing power and huge understanding capabilities of the machine learning models. So the large language models, at least they show that maybe the personalized medicine is going to be in the near future and things like that. Education, it will bring up a lot of changes in the education. We might have already seen that how to teach and guide students who have access to these foundational models. For example, now at the universities, we are worrying about how to test the students because they can use large language models to generate their assignments and things like that. So that is one of the biggest challenge, biggest things now happen. And I will quickly go through some of the challenges. All these models, they are built on the huge training corpuses, which is the pre-existing corpus. So all these corpuses, they have inherent biases. And the intrinsic bias is going to be a byproduct of using these pre-trained large corpuses. So these models, they also contain biases. So for example, they can have this racism and the discrimination about the downtrodden communities and things like that. For the model, it doesn't know anything. So it doesn't know whether it is racistic or hate speech or something like that. But on the other hand, we have to deal with them. And this is one of the biggest challenge in the language model development, how to handle these biases and things like that. Another thing which might happen is the misuse of this model. So these models can be used to generate fake content, and it is very difficult to identify the fake content. Now we can use these models, for example, to generate fake tests, for example, fake profiles and things like that. You can also use several generative models to generate fake images. And so the coming years will be flooded with a lot of fake generated content. And our research shows that it is quite hard for humans to identify the AI-generated harmful and manipulative content. So in the future, it will be really big difficult to identify whether it's in fake news or real news and things like that. And then we also have seen what social media has created. Social media is mainly purposed to give power to the people to express themselves, but it has created several adverse effects in the society. You can see here. For example, you can see the addiction, disinformation, mental health, and polarization, especially censorship and things like that. And what happens if we empower these models with a lot of AI? So now we are giving huge capabilities to these huge social media and things like that, right? So then it can create a huge problem. For example, bias and taking away jobs and other kinds of things. So this is a pretty good video, you can say, from the Center for Human Technology, talking about the technology and the responsibilities and things like that. When we invent a new technology, we uncover new class of responsibilities. If the tech confers powers, it starts a race. And then if you don't coordinate, then it will race will into a big clash. And this is my last before slide. So now we can see that the race has already begun because all the big companies, they invest huge amount of money in the research and things like that. Now we know that Elon Musk is also in the race. So now he's saying that he started a company called Truth GPT. Initially, he didn't believe that the large language models is good and things like that. Now all of a sudden we started developing one more thing. So the war has already begun. The worrying fact is most of these models are being developed on the private sector, where the transparency and other kinds of things is a big issue. But on the other hand, if you compare the universities, they don't have huge amount of resources like these companies. Because if you want to try large language models, you really need billions of dollars. And on the other hand, these companies are investing huge amount of into that. So let me conclude. So we have been living in quite interesting times, and so we have to see how things will evolve. And we have been witnessing the exponential growth in AI, especially in the last 4 to 5 years. I'm talking about large language models and their capabilities, so which will create a lot of transformation in society, both not only in our lives and how do we use content, how do we generate content and things like that, but also it will bring a lot of changes into the society. And so sometimes if we don't harness these technologies properly, then they can create a lot of concerns, risks, and harms to the society. And so what we need is we need a dialogue to harness this technology. Many people compare these technologies like the nuclear power, right? When we first invented nuclear power and made bombs and things like that. So the technology is innocent. It could be used for both the good and bad purposes. But it is the people behind it, how do they use and things like that. So we need a dialogue to harness this, how to use this AI revolution responsibly. I'm sorry about the overtime. I thought of leaving some space for questions. Yeah, thank you so much for listening. If you have any questions, I will be happy to take it.
Hello.
Yes,
Yes, sir.
please
It's
go ahead.
a very nice, informative session, sir. But I'm having one doubt regarding the large language models. You said that that's a personalized medicine, right? So that is based on our genetic model, how the medicines are personalized. Because nowadays, each and every medicine that is common for some age group, like So it is
Yeah.
possible, sir, in real time.
Yes, that requires a lot of genome processing, right? Like processing of the genetic profile. So that's why it was not possible before. For example, what we do is we follow this one size fits all the approach. So, for example, let me give you a very informal example. We go to a shoe shop, let's say we want to buy a shoe, and we go to a shoe shop and we just buy shoe, not looking into our which size fits to us and things like that. So the current medicine is you have the pretty standard predefined the procedures based on the disease. So the same medicine will be given to all the people. But when we have the personalized medicine, then our genome genetic profile will be analyzed, and based on that, we will choose the right medicine with right dosage and things like that. So it might be different from two people. The same disease, you might have different drugs with different dosages and things like that. And not only that, it will also build up new opportunities rather than having the medicine treatment plan and things like that. You can also devise prevention plans. For example, let's say that people are becoming obese and susceptible to diabetes and other kinds of things. Then, based on the genome profile and the lifestyles, it can design a treatment process so that you don't end up into diabetes and things like that. But all these things they require huge amounts of processing power and huge powerful models. So it is the expectation that large language models will try to solve these problems because now all of a sudden we have huge enormous power.
Yes. Thank you, sir.
Sir, am I audible?
Yes, yes, please, yes.
So, on behalf of Department of CSC, VNR VJIT, and all the participants, I would like to extend my heartfelt thanks for your exceptional keynote address on generative AI. Your insights were incredibly enlightening us and has given us a deeper appreciation for a rapidly evolving field. And I understand the meaning behind what is AI yourself. I think it is both in a good direction as well as in a bad direction. Your expertise in generative AI and the case studies mentioned are truly commendable, and this will help us in enhancing the quality of the projects that we'll undertake at both UG and as well as PG level in various domains like social media, healthcare, biomedicine, NLP, in all these directions. And also, probably our faculty and the students look for publishing a quality papers in this direction, and we can understand what is the research scope in this area. We would like to stay connected and continue learning from your expertise. Please be with us, sir. Thank you very much once again for your keynote delivery. Thank you, sir.
Thank you so much for your invitation. Thank you so much.
Thank you, sir.
I wish good luck for the conference. Yeah.
Thank you so much, sir. Thank you.
Now I will disconnect. Thank you. Bye.
Yes.
Sir, am I audible? Rahul Garu,
Hi,
am I audible?
yes,
Yeah, sir.
yes, you are.
Yeah, sir, good
Thank
morning.
you.
Welcome to ICACECS 2023.
Thank you. Do you want me to start sharing?
Yeah, 1 minute, sir. I will introduce you, sir, to the
Sure. Thank you.
participants. It is an honor and privilege to introduce Dr. Rahul Boyapati, United States, to you all. Dr. Rahul Boyapati Sir Garu serves as a hardware engineer at Tensterent Inc., Portland, United States, focused on architecting cache-coherent networks on-chip and large-level caches for RISC-V CPU cores
targeted to be utilized in the next generation AI hardware. He completed his PhD in computer engineering and ME in computer engineering from Texas A&M University in May 2017 and BTech in electronics and communication engineering from National Institute of Technology, India in May 2008. He has published many papers in international conferences and journals. He has worked on designing a state-of-art grounds-up RISC-V architecture-based CPU systems. He has developed and implemented novel cache-coherent, last-level cache, and network on-chip solutions for interconnecting CPU clusters. He played an instrumental role in defining and architecting CXL IP for Intel's next-generation server chips. CXL was a ground-up, industry-supported initiative for a unified, cache-coherent, interconnected, aimed at processors, memory expansion, and accelerators. He worked on several critical performance and design-related challenges in building a state-of-art IP block to facilitate a low-latency, high-bandwidth interconnected for plugging in future Intel accelerated products. He works extensively on pathfinding and implementing the tools required for low-cost formal verification of common mesh stop using Jasper Gold. He designed an assertion-based property verification methodology for the module, which led to significant corner case defect findings. We welcome you, sir. It is an indeed honor and pleasure to have you here today. Please join me in welcoming Dr. Rahul Boyapati Garu to deliver the keynote speech. Thank you.
Thank you for the introduction.
Thank you, sir.
Give me one moment. So, can you let me know when you actually see the...
Yeah.
Okay, perfect. Yeah, so hey, I'm Rahul. It's it's a privilege to speak here and give a keynote address to this conference. So I would like, and I was actually listening to the previous presentation, and I think this would be a good continuation from that. So I think the previous presenter was talking about generative AI, and
Sorry to interrupt you. Can you kindly switch on video for a few minutes, sir?
I have a problem with my video. Give me maybe like halfway through it, I'll try to figure out.
Right.
Yeah, sure.
Thank you, sir. Thank you.
Yeah, no worries. Sure. So let me continue. I just want to continue on that same topic of generative AI, but I work more on the hardware side of supporting these AI models and how we are creating the next generation servers and the chips behind the machines that actually run these models. So there's a huge shift in the industry, especially the way I would put it is in the early 2000s everyone was focused on single core performance. So you'd have a processor and everything was like an application that would run on single processor. Slowly, maybe around mid 2000s, there was a big shift when people started building multi-core machines. And I think that was a drastic shift in how hardware was built and leveraged. Then the next big step that happened was with GPUs and NVIDIA, where they were actually able to build a software model, which is CUDA. I don't know if you if that's familiar, but that kind of built NVIDIA into the company that it is today in terms of running AI, and they are kind of the leaders in terms of AI hardware at this moment. So I just want to speak a little bit about what are the big changes that are happening in the industry to facilitate these AI models to run on hardware, and specifically to focus on something. I actually want to talk about how we are building huge SoCs, systems on chip, and we are hitting a limit in terms of how we can put all of these transistors onto a single chip and what is the solution that people are going towards. And that's kind of where the interconnects come into play. So I'll probably get started with a little bit of so the agenda I want to go over is, and I think the presenter bio is going to present, but I think the bio Iga is gave was better, so I'll just skip that part. Um, I'll just go over the current state of the art high performance architectures, then move on to some of the hardware design challenges that AI models have brought in, and why the current state of the art system architectures won't work anymore, and why most of the companies, hardware companies, are shifting, and, and that's shifting towards something called chiplets. And I'm going to talk a little bit about what chiplets are, and just introduce you to some of the chiplet interconnect protocols, and that's what my real focus is on. But I'll give you a very high level overview of it and why that is important in today's world, and it's going to be important going forward. So let me get started with the current state of the art high performance system architectures. And just as a please feel free to stop me if you have any questions and something's not, because I probably want this to be a little more interactive. So just, yeah, you can just stop me anytime and ask me questions. So to start off, I'd go over what we call a systems on chip today. What a system on chip really is a mishmash of different things that used to be like a big package. What I mean by that is, in earlier days, you used to have a processor on a chip. Then you used to have some I/O components on a separate chip. You used to have a separate memory. You used to have separate controllers for mouses, keyboards, separate device controllers and stuff. All of it has moved onto a single system on chip, and this has been the norm since maybe the last 15 years, I would say. So all of the high performance server grade chips that you see today in most of your data centers, this could be Amazon Cloud or Google Cloud or any of the data centers, will be some kind of manifestation of a pictorial view of this SoC. So the picture I'm showing you here is from a company called Sci-Fi. It's just a simple picture. Any company's SoC, you could take it and it would kind of look similar. So you'd have a cluster of CPUs, which means just a group of CPUs, and then you'll have a scalable coherent interconnect to maintain cache coherence between these CPUs. And then you have a shared last level cache, and different companies have different versions of this. But the high level overview is you have memory integrated into the whole system, and then you have a large number of parallel CPUs working, and you write applications which can use this parallelism. So this is where most of what we've been doing in the last like last decade has been. Now, so another example that I would like to show you is something like Intel's Xeon processors. This has pretty much been the gold standard until like maybe 2-3 years ago in every server system, right? So this is kind of how like an Intel Xeon server actual architecture looks like. You'd have, so this SKX is a Skylake, that's their code name for their server product and server CPU. So you'll have a bunch of these CPUs with their own last level caches, and they're all connected through these red wires, which is the interconnect. And you have a bunch of PCIe and stuff like that to connect your memory. So this is how they build their servers. And multi-socket SoCs are kind of connecting a multiple instances of these servers on a single. So a single server would go on a single socket, and then you would connect these sockets through interconnects. So this is how you build up like big data centers, right? So this has all been good and going good. So now why change, right? What's causing the change? What are the hardware design challenges that AI models are bringing in that's causing all of these companies to shift and change from something that it's well and truly tested? So a couple of big things, and I think the previous presenter kind of went over this a little bit, so I won't dwell on it a lot. Is the next generation servers will be required to process big data, right? So it needs huge amounts of memory and memory bandwidth, which is which is really hard to get today. Memory bandwidth is probably the hardest thing to scale in terms of processing nodes when we go from, when people say 5 nanometer, 7 nanometer, 3 nanometer, as we scale, compute power scales really well. You can pack a lot more computational power, meaning CPUs, into the same area in a chip faster, but memory does not scale well. So having memory bandwidth is premium, right? So that, then the problem with big AI models is they do need large amounts of memory. So that's the first problem. The other is, even though we are able to pack a lot of compute power, AI models need a lot of parallel compute power. They might not need the same thing that you need on a regular application that you run, right? So what, how do we solve these, right? So the one way to solve this is, people go to an extent as to say, why not pack more and more compute power into a single chip and make SOCs bigger, right? But the problem with making SOCs bigger and bigger is there is a reticle limit in how big a single chip can be, in terms of, I mean, purely a function of cost versus the yield that you get from making these chips. So you cannot make your SoC bigger than a certain thing, right? So the other way people have thought about solving this problem is, why not just disintegrate the SoC into, again, go back a step, have smaller components in the SoC, and then have something called packaging technology, where you run, and I'll show you a picture of it, but it's essentially an advanced packaging technology, and this is really what's driving most of these changes, and the most costly thing today in the world, which is where TSMC is kind of the leader in it, and why everyone's makes their chips through TSMC, is connecting some smaller versions of these chips called chiplets, and putting these different functions that we talked about, like memory, right, different kinds of compute on each chiplet, and connecting them through something called a packaging substrate, like I show here. So what you do with this is, you do not have the cost penalty of going from a chiplet to chiplet. The biggest drawback of this is, you have some model that needs to run on this whole chip, but it needs some communication from like the one quadrant to the other, right? So the communication, once you go past a chip and you go onto the substrate, is going to be slower. Previously, in older systems, when you had to do this was expensive because of the latency. So performance wise, nobody was willing to take a hit like that. But now with these advanced packaging substrates, you can mask most of this, and some software changes and some compiler changes can also help you mask a lot of this latency. So once you do that, the advantages chiplets bring are enormous, because and I'll go over some of them, but just to step back a little, what is a chiplet, right? Chiplet is just a smaller version of a chip, but it does not contain the whole function of an SoC. What it's kind of doing is, it's kind of breaking the SoC into parts. So you're kind of breaking some bigger thing into smaller parts, making those smaller parts and stitching them together on a package. But you do, it's not as simple as the smaller parts are just stitched together and they work seamlessly. They have to be designed to be able to stitch together, and they have to be able to talk through a protocol. It's not just simple wires. So that's where most of this complexity and the new research comes into play. And how do you make it, how do you make it work, and how do you write your software models to make sure you take advantage of the locality of a particular memory which is closer to a particular part of the chiplet and stuff like that. So big reasons to going to chiplets, heterogeneous architectures is one big thing. In previous SoCs, all you used to have was CPUs. Now with chiplets, what you could do is, one of your chiplets could be a GPU, another could be an AI accelerator, another could be a CPU, and you can plug all of them together into a single SoC and provide that to the customer, right? And that can be, and your AI model can take advantage of whichever is more conducive, to be for its specific use case. Composability is a big thing. One thing in chip industry is any advanced node, and today we are talking about 3 nanometer nodes, is top of the line and it's very expensive. Only the high-end companies like Apple, Intel, Nvidia, or AMD can afford to buy it. Even, I mean, sometimes AMD also has to step back a little. So it's very expensive to always be on the leading edge node. So you always are trying to save costs when you create a product by being a step behind, right? For example, today 3 nanometers is the state of the art. So a lot of chips today are made at 6 nanometer node. A lot of these chips that you use in cars or like this autonomous driving, they are made in 20 nanometer node. They're three steps behind because it's cheaper. It's cheaper and it's truly well and tested. The latest nodes are always expensive because you also lose a lot of chips to defects. So now what does chiplets have to do with this? Well, the big thing is these all 4 chiplets do not need to be in the same node. You can actually only make one of these in the most advanced node, depending on, like, let's say your CPU is your most important part of your machine. You can make the CPU in the most advanced node, and the rest of them you can go back a step, right? And that helps you in terms of cost, in terms of higher yields in production and everything. Yeah. So that's another big advantage of using chiplets. Now, the next part is the democratization of technology access. This is a big thing. Most hardware, so the biggest reason you do not see a lot of hardware, you have not seen a lot of hardware startups versus a lot of software startups that you see is because it's expensive. It's expensive to start a hardware company and actually produce a chip. And most companies don't own fabs, right? There's only 3 fabrications companies in the world, right? It's TSMC, Intel, and Samsung. Only those 3 can actually make a chip. Everybody else is designing a chip and passing it on. Nvidia makes their chips through TSMC, AMD makes their chips through TSMC, Intel has their own foundry, and they actually use some TSMC. And everybody else most likely uses Samsung. Even Qualcomm uses Samsung. So fabs are expensive. Designing a chip is expensive. So what does chiplets have to do with it? Well, now in the last 4 years, you see a lot of hardware startups, and I'm working at one of them, right? So all these companies do not need to design their whole SoC. They can design what they're good at, and if they, and this is where I'm going to talk about, is the interconnect protocol. If they can adhere to a protocol on their pins, which is, think about it as a language, right? Let's say today I want to be part of a group and I speak English, right? So I can be part of the group. But if the group speaks German, I can't be part of the group. So it's something similar, right? So if I design my own chiplet with my function that I want to put in hardware and can actually expose a particular interconnect protocol that everybody else speaks, then I can build an SoC or a system with chiplets from other companies that I can buy. I do not need to build them. Sometimes just licensing them is cheaper, right? So it affords, chiplets afford, give this affordability to a lot of new startups to explore their function by not having to design their whole SoC, but designing their function and maybe just selling their own chiplet or building an SoC using other people's chiplets, right? So it's kind of democratization of technology. So that's another big thing, and that's why we are seeing a lot of investment in hardware startups, especially because of AI and this chiplet paradigm in the last 5 to 8 years, and that's reaping benefits now. The other part, and we talked about this, is memory, right? So how does chiplets help with memory? Well, when we talked about this packaging technology, the other big thing packaging technology gives is, this is part of what we call today as 2.5 dimension or 3D packaging. So you can actually put memory on top of a chiplet. So memory is, right, you can actually, it's expensive, but it's called HBM or high bandwidth memory. And this is what most new systems use. And I'm going to show some pictures of examples on that. And they just put memory on top of your chip. So it's fast, it has very high bandwidth, it's expensive, but it works. So this whole paradigm opened up the memory integration being closer to the chiplet, so it gives low latency and high bandwidth memory, which is the call of the hour for most AI processors. And I'm going to just show you some examples of chiplet-based systems that are already in production today. They do not have a standard interconnect protocol because these were designed by most of these companies in-house. And only now do all of these companies see a need to have a universal language that they speak. Until now, it was all proprietary. Everybody had their own thing, and they designed their own chiplet-based systems. And this is out now. This is called Intel Sapphire Rapids. This is their latest. This was released, I would say, 6 months back. This is their latest and greatest server chip. What you're seeing here is, if you see this picture, I know it kind of looks blurry, but you kind of vaguely see four big partitions of this chiplet. They are actually four different chiplets. This pink colored EMIB5, it's called EMIB. It's embedded multi-die interconnect bridge. So this is Intel's own proprietary bridge to talk between chiplets. So what you're seeing here are four chiplets, kind of like this picture, connected on a packaging substrate. That is what is really happening here. And on a single chiplet, and the right-hand picture kind of shows a cleaner representation of it, where you have, these are four chiplets, and the orange wires are the EMIB, the connections. So you have, on each chiplet, you have a bunch of CPU tiles. This is not heterogeneous computing, where I talked about one of this could be CPU, one of this could be GPU. It's not that, and I'll show later pictures of something like that, but this is just a replica of four systems, all CPUs, with caches and memory. And what you're seeing in this smaller picture over here is what I talked about, is that packaging, right? So what you see is on the top, on the die 1 and die 2 are the silicon chips. They are actually the CPUs. And what you're seeing underneath that is what we call a silicon bridge or packaging substrate. This is new, and this is what's really expensive today. This is to connect. This is how these chiplets get connected, and this is the reason why it's fast to communicate between them. If you go over the die on the top, it's kind of like PCB board connections, and they're slow. So this is fast. So this technology is new, and it's used in all of the big companies, hardware companies' products on their latest and greatest products. So this is an example of Intel's Sapphire Rapids. This is their top of the line server product. So they use chiplets, but they use their own proprietary protocol, right? So, and I'll talk about how they're changing that to something more standard. Similarly, you look at NVIDIA. This is their latest and greatest. This is called Grace Hopper. This was, I think, even more recent. This was released in the last 3-4 months. So what they have is a CPU on the CPU chiplet, and this black picture on the right hand side corner kind of gives you a better representation. The left hand side is a CPU chiplet. The right hand side is actually a GPU chiplet. So they are interconnected using what they call as NVLink. Again, it's a different protocol. It's their own proprietary protocol. It's a cache coherent interconnect between CPU and GPU, and this is released as a super chip, right? So this is going to be in, and this is what they call as H100. It's codenamed Grasshopper, but this is one of the most expensive chips available today, and thus it's in like the highest demand for AI processing. So most of, like, I would say at least 90% of AI processing today runs on NVIDIA chips in the world. So this is what it really runs on right now. So this Grasshopper CPU GPU chiplet system. Next one I want to show is, this is just coming out. So there's not too much information on it. It's been released, but it's not yet in, it's just been presented. So I don't know if it's already out and running, but this is from AMD. It's called MI300X. This is a heterogeneous system, just like the previous one, where it's a CPU, GPU. So what you see here are these the turquoise boxes in the middle. These are these CPUs and GPUs combined, like they're all together. This is a picture. This is not clear because there's not too many details out there, but what you see that's denoted as HBM3, that's high bandwidth memory. This is what I was talking about with the 3D stacking. You get high bandwidth memory, it's expensive, and people only put it on the top end products. but it's really fast memory. It's at least an order of magnitude faster than DDR, which is the standard for memory today. So this is AMD's system. Again, their interconnect, you do not have too many details because it's proprietary, because all of this is designed in-house by AMD. Now, what is the biggest challenge with chiplet ecosystem, right? True disaggregation of chiplets and plug and play flexibility, like we were talking about, where everybody designs their own function on a chiplet and they want to build an SoC by using chiplets from somebody else, right? The biggest like hurdle today is how do you connect to somebody else's chiplet? How do you both speak the same language? How do you connect to each other? How do you use the same lanes to connect, right? So this needs a standard interface protocol definition specification across the industry. And so this has gained traction, which culminated in, I think this has been close to an year and a half back, where two consortiums were formed. One is called Universal Chip Interconnect Express. And this, I would say, is the top runner in terms of having the most traction from most of the industry. And I'll concentrate a bit more on that. And then the other one, namesake, is Bunch of Wires. It's from Open Compute Project. This is an open source compute consortium, and they do have other stuff. It's not just this. That's open source, and anybody can look it up. And so I think I'm just until now I was just trying to set up what is really a chiplet ecosystem, and kind of why do we need it, right? What's the importance of a chiplet ecosystem, and then why do people care about interconnect protocols between chiplets, right? So the point is chiplets are important, and that's where the way the industry is going. Like just like you saw with all of these examples, every hardware maker's highest end product today in the market, which I mean like this year, is made of chiplets. And nobody has monolithic SoCs anymore. Those died like 2 3 years back. Every product is a chiplet based system, and now people are seeing the importance of having a standardized interconnect protocol between the chiplets. So the first one, and this is probably going to be the winner, and it's going to be called Universal Chiplet Interconnect Express. It's formed as a consortium by the same people that formed PCIe and CXL. It's the same consortium. It's run by all of the big companies, hardware companies in the world, right? So all of them have a stake in it. It started at Intel, but every one of these companies have a stake in it, and they all ratify a specification so that you have a specification and everyone adheres to it. So the idea behind UCI is fairly simple, right? We create a standard interface for a chiplet so that any chiplet can connect to it, and it supports any kind of packaging. It doesn't put restrictions on, well, you have to run at a particular voltage or you have to run at a particular frequency and stuff like that, right? So it has a level of variance built into the protocol itself and the definition of it, so that it's a wide range of things that can be supported in terms of hardware. So like I was talking about, they support 2D. So standard package, and I think we were talking about this, I mean, touched on this a little bit earlier. A standard package is just connections, something like this on a package substrate. So advanced packages, and I was showing you an example of EMIB or EMIB earlier, is something essentially where you create a silicon bridge in the packaging substrate to get faster path between a particular die to a different die, right? And these are advanced packaging options. There are different ones. Every company uses something different. I know for sure that TSMC today uses this COWOS. It's called chip on wafer on substrate. So this is what TSMC uses. EMIB is an Intel thing. So Intel uses this EMIB. So these are different variations to achieve the same thing. Everything has its own benefits and disadvantages, and I'm not an expert on entirely that, so I'm not going to spend too much time on that. But just to go over like a high level of what a specification like this defines, right? So what does UCIe really define, and what does it mean? So UCIe defines 3 layers of protocol stack. So what it defines is very high level a protocol. Actually, let's start from the top bottom, right? So first things first, it defines what a physical UCI layer needs to look like. It talks about how you do your link initializations, how you first, I mean, even simpler than that, how should your electrical and AFE kind of look like, right? What kind of sideband and stuff should look like. Then it talks about what are your different lanes, how would you do your link initialization, and I won't go into too many details of that, but I'll have some more details in the next slide about this. But it defines a physical layer on how you actually have a physical like connection between two chiplets. Then on top of that, you build something called a die to die adapter. This is like this middle layer which kind of puts something from the protocol layer, which is very very high level. It's kind protocol layer, you could think of it as a language, right? So the protocol layer is a language which is trying to speak in words, and then the die to die adapter puts it into alphabet, right? So it kind of puts it into letters, and the physical layer is actually just the writing on a notebook. So it's kind of like a translation. The protocol layer is the understanding, right, between two chiplets in terms of you read a word and you understand it. The die-to-die adapter is the letters, right, and the physical layer is actually the medium that conveys those letters, right. So the die-to-die adapter has the middle part where it takes care of all of this link management, parameter negotiation, and a bunch of this stuff. Not going into too many details there as well. But a protocol layer, UCIe supports PCIe protocol. If two chiplets want to talk through PCIe, it supports that. If two chiplets want to talk through CXL, it supports that. And these are all different protocols. I don't think I'll go into details on what these protocols are, but UCIe supports them. And there's a mode called streaming. All this means is you create your own protocol. If you know that you're designing two chiplets, but you still want to use UCIe, but you want to talk your own protocol, right? You can do that. You can just, if UCI won't translate anything, it will just give you space to just stream whatever you want to stream. So that's the streaming part. It's just raw, like metal layer bits that you can transfer from one stack to the other. So that's at a high level what any protocol would define. An interconnect protocol would define, right? So a protocol layer, a die-to-die adapter, and a physical layer. So if you look at a little more details onto what a UCIe physical layer would look like, you'd have, and this is kind of die 1 and this is die 2. You have these main band and side band, so we won't go too much into that. But this is how your connections would look like. You have a bunch of signals, like you have the clock that you send from one to the other, and then you have the data. And when I say data, it's just anything that you want to transmit, right? And then you have these tracks. And again, I won't go into details on this, but this is how the file layer itself is defined. So anybody who is implementing UCIe and they want to adhere to this, they would adhere to, and I'm just showing very high level details on this. There's a whole specification that's open source. Anybody can go read it. It's a consortium page. You can just look up UCIe and it'll show up. It's fairly simple to get the specification. And it has way more details on it and how you want to construct this. So again, the adapter layer is the one that does, and when I say link initialization, I've been using that word, but what this really means is when you connect two chiplets, they both have to discover what's on the other side, because you're just connecting, you might be connecting to something you built on the other side or somebody else built, but all you know is it's also UCIe. So there are messages that you can pass and kind of figure out that, okay, this is what the other guy is doing. Like, is he talking CXL, is he talking PCIe, or what is he going to talk, right? And then you can configure your own UCIe controller to do the same thing, right? So that's what I'm talking about when you say link initialization and the protocol and die capability discovery. So there's a whole lot of details that go into it, but think of it as you're waking up and you're figuring out, you're passing messages to the other guy. You pick up the phone, you pass a message and say, okay, he's speaking the same language as me, or he's speaking a different language, so I need to move, talk a different language. So you're figuring out what each other is doing. Once you figured that out, that's when you pass it on to the protocol layer. The protocol layer is just going to say, okay, this is very high level, where this is what a whole system level manager would do, right? Like coherence protocols or anything like that. So the UCIe defines that you can talk, it will support any of these, or you can just stream anything. And in the future, they're also planning to add support to a bunch of other protocols. So they want to support as many protocols as possible onto this, so that it just provides more flexibility. Right. And the importance of UCIe, well, this week, the Innovation event happened. They kind of showed, Intel CEO Pat Gelsinger, he kind of showed this Pikes Creek. This is the first UCIe IP chiplet. It's fabbed on, it's a CPU that Intel built, and they used UCIe. So they're moving their processors from their own internal protocol to UCIe, and they built it on Intel's 3 nanometer process node. And on the other side, they took a Synopsys UCIe IP fabbed in the TSMC 3 nanometer node, and they built one chip. And this is a test chip, but it's a CPU chip called Pike Creek. And they were able to establish connection between these two, and they demonstrated an actual working chiplet, right? So that's big, because they're actually showing that UCIe helps you, because one side of the UCIe die zero was designed by Intel, and the other one was designed by a completely different company and fabricated on a completely different company's node, right? So it's complete two different chiplets put on a single package and working together, right? So that's kind of where the industry is going, and they kind of showed a test chip. And this happened, I think I added this for a slide today because this event happened 2 days back, literally. So that's kind of where UCIe is going, and this is most likely going to be the winner in terms of chiplet interconnects. I mean, this has the backing of every big company there is, right? But at the same time, there is something called bunch of wires. It's named that, but essentially all they're trying to do is they're trying to say we do not want the overhead of any industry support or any, because so the advantages of a consortium with all of these big companies is that you have financial backing and you have people who are willing to use it, right? So you actually have products made out of it, just like we were talking about with Intel's Pike Creek. The disadvantage is when you have these many big companies in a consortium, things move slow. Everybody has their own agenda in terms of what they want to push and what they do not want to push, because any change in a specification has to be adhered by everyone here, right? So things don't move fast, things move slow. So this is the overhead, and sometimes to appease people, to you kind of have to make trade-offs where a bunch of different things get added. Like you add 10 different 10 different things onto a protocol, and every company needs one different thing, right? But you have to support all 10 because you don't know who you're connecting to on the other side. So it becomes, there is a lot of overhead that comes with it, and a lot of that's a way to put it. Like there's a lot of overhead that comes with it. So a bunch of wires goes the opposite way. Open Compute Project is a research project. It's not entirely research. It is kind of supported by some companies, but mostly startups. And their idea is we want to keep it as simple as possible, right? We do not want a lot of link initialization overhead, a lot of protocol support and everything. We always want to do raw metal based stuff, and we do not care about what protocol you want to do. You take care of all of that overhead, right? So we're just building, or we're just going to specify how you connect the physical layers, right? So bunch of wires is very, very straightforward. All it does is it tells you how you connect two link layers, and that's it. It doesn't talk about protocol layer, it doesn't talk about anything. You are free to do whatever you want to do on top of it. This gives a lot of flexibility to a lot of people because this is lightweight, but at the same time, this also opens up um, to a lot of issues, because there's going to be gaps in terms whenever specifications are light, it's helpful in terms of building something fast, but it's also going to be detrimental because there is not a lot of actual specification in it, right? So that's the drawback of a bunch of wires. But you also have a lot of companies supporting or using BOW. But what you'll see with this is, except for Samsung and NXP, most of the companies are small or startups. So everything has its own benefits and disadvantages. So we'll have to see. But most of the weight of the industry is behind UCIe. But yeah, that's where this is. So just to kind of give a conclusion on this, yeah, I mean, AI compute is fairly understandable that there's a huge demand for high performance computing and memory capacity. Monolithic SoCs, this has been what we've been doing for the last 15 years. It's just become too big for effective manufacturability. And also, there's other advantages by disaggregating designs. So, especially process nodes that we talked about. So, product composability, there's a huge appetite for it across the industry, right? So, this is kind of driving chiplet based designs, and we're seeing a wide adoption. I mean, UCI and BOW seem to be front runners, and out of these two, I would say UCI is. So I just wanted to kind of give an overview on where the chip industry is going and why some of these interconnect protocols have become a necessity right now. So yeah, I open the floor for any Q&A. Yeah, I just wanted to leave 15 minutes at the end and have some backup slides, but I didn't want to go over it. And I'll try to find a place to turn on my camera. Give me one moment. So do let me know if you have any questions. So
Yeah. Hi, Rahul.
hi.
So, is there any standard or common communication interfaces between chiplets? Yes.
Yeah. So I think UCIe today is going to be that, but until now, I don't think there is anything standard. Most of it has been every company has done their own independent thing. It's not exposed. It's not open source.
Okay, then how much space is required for interfaces?
So space wise, I would say it's not, space is not a big problem because these are off chip. So these are going out of the chiplet. So you have enough pin space for most of these, just kind of like similar to PCIe lanes and stuff. So I don't think space is the big problem. It's more of the latency is the big concern for people when you're going off chip. There's more than I think enough space for the pins.
Thank you. So your
Yeah.
video is somewhat little bit dark. Could you please?
Yeah, I was trying to figure out. Give me one moment.
Okay. Yeah. Thank you. Thank you, Rahul.
Yeah. Okay.
Rahul?
Hi. Sorry. Yeah. Give me one moment. I'm just trying to turn on my camera. Yeah, I think this should be better. Hopefully. So any other questions or?
Rahul?
Yeah.
Hi, how are you?
Good.
Yeah, the question is already done. Now, one of my colleague has asked a few things on it.
Okay.
Basically, when we teach the computer organization subject, probably we can get in-depth knowledge about today's delivery. But anyway, it was
Sure.
bridging the gap at the software end, what we have been doing, and how would the hardware react to it.
Right. Yes. Yes.
Thank you so much. Thank you very much. Teja,
Thank you.
are you online?
Yes, ma'am.
Yeah. I hand it over to Teja for the vote of thanks. Thank you, Rahul, once
Thank
again.
you. I stand before you today with a deep sense of gratitude and appreciation as we conclude this enlightening session on the state of our high-performance system architectures. We had the privilege of delving into the intricacies and advancements in this dynamic field, thanks to the expertise and insights shared by you, Rahul sir. You have enlightened us with your profound knowledge in the system on chip and chiplets. Your presentation are not only informative but also inspiring, and we are truly thankful for your valuable contributions. The today's innovative session provided us with a deeper understanding of the cutting edge technologies and trends that drive innovation in this field. I hope that the knowledge gained here today will inspire all of us to explore new frontiers and push the boundaries of what's possible in universal chiplet interconnect expresses. Thank you and have a great day.
Thank you, and good luck for the rest of the conference.
Thank you, sir.
Rahul, you can sign off.